All right, today it's spring 2021, and we're going to do this problem. A Venturi meter is a device in which pressure energy is converted to kinetic energy. Okay, so basically you've got pressure in this wider portion of this pipe, over here, and it's being converted into kinetic energy by basically going through contraction. By going through the contraction, it speeds up, and so it becomes kinetic energy. To measure the flow rate of liquid through pipes. Okay, so this is all just a bunch of history of the Venturi meter. What we want to know right now, so this is our givens. We've got this picture, and we've got oil. So S oil equals 0.86, flows through a 30 centimeter section, and through the contraction. The contraction is 15 centimeters. So we've got, clearly this is not really drawn to scale, but this is 0.30 meters, and this right here is 0.15 meters, okay, diameters. Okay, let's see here. Okay, so required, we want to know A, compute the volumetric flow rate of the oil, Q equals what? And B, if instead of the oil, if the pipe, so basically if water at 50 degrees C, what is the pressure of the Venturi? P equals what if cavitation? Okay, so the second part's actually quite simple, although it will probably throw you for a loop if you hadn't given it much thought. So we will get to that. Okay, so here's our solution. Okay, so let's see. We know right off the bat that, this already tells us it's going to be Bernoulli's equation. But it seems very logical that we're going to want to use Bernoulli here because we've got basically a contraction here. You might use energy equation later in the semester, but we don't even know the energy equation right now. But we're trying to get at flow rate, and the Bernoulli has a lot of the things in there that we care about. So typically I use the Bernoulli as my master, P1 over gamma plus Z1 plus V squared over 2G, so that's a 1 equals P2 on gamma plus Z2 plus V2 squared on 2G. Okay, we can't get rid of any of these terms because at any of these locations, so if I look at point 1, I've got a pressure, I've got an elevation which is 30 centimeters, and I've got a velocity, right? And the same thing can be said for location 2. P1 is, there is a pressure here, as indicated, amongst other reasons, like we've got a manometer here, so that's telling us that there's a pressure here. But really, we're just inside of a pipe that's full of water, so we know it's got to be pressurized. We've got Z2, which is 25 centimeters, and we've got a velocity. Okay, so this thing doesn't lend itself to easy solving. However, as you guys have noticed by now, this is one of my favorite types of problems. Okay, so let's go, and we're just going to start with let's start with the manometer, okay? Because we're just going to kind of go in order. So we want to kind of get at these pressures. Okay, so the manometer is how we get at pressures, and so we're going to start at P1. Okay, and then I'm going to move upwards. Okay, so I'm going to move up this way to there. Okay, now that's a little confusing, a little tricky, right? Because I need some distances. Okay, so you have to not be afraid to come up with some variables that are going to be useful for you. So I'm going to call this little distance from here to here, I'm going to call that lowercase h, and I'm going to call this big H. Sometimes these are called H1 and H2 or whatever. It doesn't really matter. But the point is I'm starting at point 1, and I'm going up by, let's see, so I'm going up to here. So I'm going minus gamma, this is oil. Okay, going up by capital H, plus that 18 centimeters, 0.18 meters. Okay, so that's going to get me to here. Okay, I'm going to jump across here. That doesn't matter because I haven't changed fluids and I'm at the same level. And then I'm going to go down. So I'll add gamma air times that 18 centimeters times that 18.18 meters. Okay, and now I'm going to start jumping all the way back down to here. So we're going to be adding. And that's going to be gamma oil times H plus H, big H plus little h. Okay, and that's going to get me all the way to P2. Okay, we'll note that gamma air is really small. So we're going to get rid of this term because it's very small. If you want to include it, you may, but you'll see that it's not going to change the answer really at all. And then algebraically, let's see, this capital H, this gamma naught capital H plus right here is going to cancel with this gamma naught capital H there. It's not a naught, it's an O, right? But so I apologize. And then what I'm going to do is I'm going to subtract P1 from both sides, so that gets rid of that. And I'm going to divide both sides by the gamma oil. Gamma oil. Okay, so this is gamma oil, this is gamma oil. All right, so this goes away, that goes away. And so I'm left with P2 minus P1 over gamma oil equals, looks like I got a negative 0.18 plus H. Is that right? That is amazingly simple. I guess that's what happens when you use air as your manometer fluid. It kind of disappears for you. Okay. So now we're going to go over here, and I always like this because I think this is an important point. People forget this is gamma oil. This is the gamma of the fluid that is flowing. Okay, not the gamma of some other fluid. Some people like to always make it water. There's no water in this problem. Okay, there's no reason. Water's not that special. I mean, it's pretty special. Okay, so I'm going to rewrite this as P2 minus P1 over gamma oil. So that kind of brings this over to that side because I'm going to plug in right there. Okay, now let's look at the Zs. Okay, well, Z1 and Z2, well, let's see here. Z1 is 30. Z2 is 25. So it basically doesn't matter what I put in for these, as long as Z1 is 5 more than Z2, right? So I can make this 30 centimeters or 0.30 meters, and I can make this one 0.25 if I wanted to, okay? You could also make Z2 0 and Z1 5 centimeters, and then it comes out to the same thing. Okay, so that's from the geometry. So now we've got to get at these velocities. So we're going to go over here, and we're going to do our velocities. Where is this? So we'll do that with continuity. Oh, man. It is kind of nice when there's no lines. Okay, so here we go. We've got a 30 centimeter diameter here and a 15 centimeter diameter there. So Q, we don't really know what Q is, right? But it equals V1A1, which equals V2A2, because everything that passes point 1 is going to pass point 2. So the velocity at 1, I don't know what that is, but the area at 1 is pi times 30 centimeter pipe, 0.30 meters squared on 4 equals V2 times pi over 0.15 meters squared on 4. Okay? So again, I've done this numerous times now. You can go through the algebra here if you want, but it's easiest to just note that we have, a diameter ratio of 2, which means we're going to have a velocity ratio of 4, and the faster velocity is going to be in the smaller pipe. So this will be 4. Oh, I don't want that color. Let's get rid of that. Let's do 4 V1 equals V2. Okay, V2. Come on, man. You can do it. Come on, you can do it. Just draw the little V. Just, come on. I know you're an Apple Pencil. Okay, so there you go. All right, so sweet. So now I think we have everything we need for this Bernoulli problem. Okay, so basically I'm going to start plugging all that stuff in. All right, so Z1 and Z2, I'm just going to write 5 centimeters over here. Okay, and then for V1 over 2G, I'm going to write, well, it looks like I'm going to write V1 over 2G. So V1 squared on 2G equals, hello, my Rocky dog. Sorry, my puppy is climbing into my lap. He's 80 pounds. Doesn't really work. Let me pause this. I'll come back in a second. Okay. Puppy distracted. Okay, let's see. What else do we have here? So let's see. So we've already got Z1 and Z2 accounted for. So we need V2 squared. So I'm going to do plus, and V2 is over here. V2 is 4V1. Okay, so this is going to be 4V1 squared. Okay, always remember it goes on the outside. That's like the biggest error that people make. Okay, so this is essentially our equation. We're going to start plugging in now. I guess I kind of plugged in that time, so this is a little bit unusual. Wait a second. What's going on here? Oh, all right. So through all of this, I guess I missed out on the fact that this H right here, that is, well, that's what this is right here, right? That's H. Okay, so it's 5 centimeters, 0.05 meters, right? So anyway, I'll just leave it as H because it's going to work out nice that way. Okay, so we've got H plus V1 squared on 2G. So in this case, we're in the SI system. So 2G is 2 times 9.81 meters per second squared equals P2 minus P1 over gamma oil. That's this thing. So it's negative 0.18 meters plus H plus 4V1 squared on 2G. So that's going to be 16V1 squared on 2 times 9.81 meters per second squared. Forgetting to square that 4 is probably the most common error in this class, so just be careful with that. And you can see that these H's are going to cancel. Let's see, and so we're going to end up with 15V1 squared on 19.62 meters per second squared equals 0.18 meters. And if we solve that, oh, well, we don't need that really squared now, do we? If we solve that, we get V1 equals, okay, 0.48522 meters per second, which we're going to keep with 5 sig figs because we need to solve for Q, right? Because that's what the question ultimately asked. So it's going to be V1 A1, so Q equals 0.48522 meters per second times area 1, which is pi, times 0.30 meters squared over 4. So Q equals, not a whole heck of a lot, 0.034329898 cubic meters per second. Okay, and of course, you know, the final answer should have 3 sig figs and no more. So I would say 3.43, excuse me, 3.43 times 10 to the negative 2 cubic meters per second. Okay, boom. And that's how you solve this sucker. All right, now this B part right here, okay, so that's the A part. The B part, if instead it had water at 50 degrees Celsius and it was cavitating, what is the pressure? Okay, well this is a silly question to throw in here. I didn't write this question initially. But I like it because it reminds us that A, cavitation is a possibility, but none of this matters. Okay, all that matters is we're saying that when there's cavitation, there's a pressure that like there's a given pressure for a given temperature of water for cavitation to exist. Okay, and that's called the vapor pressure. So all you need to do is look this number up on a chart. Okay, and depending on your textbook, different semesters have used different textbooks. Let me find that chart in this textbook. And for our current textbook, it is chart table 2.2. And if you look at that, it'll say the temperature at the temperature in degrees Celsius is 50, and we slide over and it tells us the saturation vapor pressure, or the vapor pressure, yeah. So it's a 12.35. So the P vaporization equals 12.35, and the units on that are kPa. And we note that this is absolute, okay? And that's a very important thing to note, that this is absolute, okay? Because sometimes, like, you might have another problem, for example, where it might say, like, okay, we've got a system and we've got a reservoir and we've got water coming out of it and it's doing all this stuff, and who knows what's going on, and maybe there's pumps and turbines and all kinds of crazy things going on, and the water's here, and it will tell you it's cavitating right here. Okay, if it tells you it cavitates right there, that's great, right? Or maybe it's not great, but you know, it's like, all right, well, we can work this problem. But let's suppose we were doing Bernoulli from here to here, right? So you might say, okay, well, this is going to be 0.1, and this is going to be 0.2, and you're going to start rolling along, and you're going to be P1 over gamma plus Z1 plus V1 squared on 2G equals P2 on gamma plus Z2 plus V2 squared on 2G. Okay, and you're like, all right, I'm rolling. Okay, P1 is 0, okay, because it's atmospheric. Cool. Z1 is whatever it is. V1 is this is 0 because it's a tank. And then you get to P2. You're like, okay, the water is, let's suppose the water is at 50 degrees C, and you plug this number in here for P2. You say, oh, well, that's 12.35 kPa. Well, you've made a mistake. Okay, you've made a mistake as soon as you do that. Okay, as soon as you make P2 that. Okay, and the reason for that is because this is absolute, and this atmospheric pressure is 0 in gauge. Gauge. Okay, as you guys know, I can't spell that word. Okay, so it's just something to be very careful of. So what you want to do is you can do either of two things. You can, in this case, it might be easier to just go, you know what? I'm not going to make this 0. I'm going to make the P1 101.325 kPa. Although really, you don't even want that K, right? So you might be 101.325 PA, right? And then over here, you've got 12.35. So we're going to, come on, give me an eraser, you punk. Okay, so you might make this 12,000, come on, you can do it. 12,350 PA, right? So that's one way to do it. Okay, now we're not working in gauge pressures at all. Or if you prefer gauge and you want this to be 0, you can make this as 0, and you can subtract 101.101.325 from this one, and you're left with negative 88,975 PA for your pressure here. Obviously, you still have to divide by gamma. And then the whole problem is in gauge, okay? And that's just, you can either work in gauge or absolute, but you just need to be aware of it. So just be aware, like that's why it's critical when you get, if you get something off of a chart, it's almost always absolute. Usually it will say so. In your current textbook, it doesn't actually say that it's an absolute. But kind of the obvious thing is it says that at 100 degrees C, it says at 100 degrees C, okay, that the vapor pressure is 101.3. 101.3, sorry, that's a 1. kPa. Okay, now note that this is when water boils, okay, is at 100 degrees Celsius, because at that point the saturation vapor pressure is the atmospheric pressure. Okay, so this is the atmospheric pressure. So just be aware of that, okay? And so that kind of tells you right off the bat, this is an absolute pressure right here, okay? It does not say 0. Okay, so that's that. And hopefully this helps you guys. And that's, 18 minutes of your lives. Hopefully it was useful. All right, take it easy, guys. All right, bye.